The morning of December the 8th began like any other routine observation cycle. The Hubble Space Telescope had been programmed to run another pass on 3i Atlas, part of its ongoing high-resolution imaging campaign. The session wasn't expected to produce anything groundbreaking. Data had been consistent. Prior images showed gradual changes, slight brightening, modest jet formation. Nothing extraordinary. So when the feed began to come through, nobody in the mission room was anticipating what would follow. At 5:42 a.m, the first composite image stitched together on the central screen, then silence. For about 30 seconds no one spoke, not because of malfunction, not because of error, but because what appeared on screen made no sense. In the centre of the image, surrounded by the expected soft haze of interstellar material, was something that looked artificial, not roughly shaped, not blurred by vapour or distortion. It was sharp, geometric, structured in a way no natural body ever should be. There were edges, not curved or cracked but straight and symmetrical. Running vertically through the object's core was a line. No, not a line, a seam. A division so exact that some of the engineers mistook it for a lens artifact. But Hubble's optical system is redundantly verified across 3 systems, and when they cross-referenced the raw data, the line was still there. Real, persistent, undeniable. Zooming in revealed more than just a seam. Around the outer shell of 3i Atlas, a repeating hexagonal pattern was visible. Not vague, not suggestive, but sharply defined, almost prismatic. It glinted in the sunlight like glass, or something engineered to refract light in calculated directions. The internal reflections bounced across the structure in ways that defied chaotic scattering. These weren't ice crystals, they weren't dust pockets, they were aligned, and that's when the room started whispering. Researchers stood from their desks, a few stepped closer to the projection wall. One analyst asked if this was perhaps a processing error, but even before the technician could respond, more frames were coming in. The object rotated slightly, about 12 degrees, and the symmetry didn't break. It shifted, yes, but the geometric alignment held. And as the shadow swept over the face of the object, what was previously assumed to be surface noise resolved into depth, ledges, layering, a sense of dimensionality that did not resemble the fractured surface of a comet or asteroid. There was no jagged terrain, no impact scars, no pockmarks from cosmic collisions. Instead, there were panels, slightly concave in some areas, convex in others, separated by evenly spaced ridges, like hatches or shell segments. And they weren't eroded, they were smooth, new-looking, impossibly well preserved. Someone in the back of the room finally said what most were thinking. This doesn't look like a comet anymore, but no one responded, not officially, because one wanted to put their name on the idea that this could be built. The implications were too large, the scientific process too strict, the margin for error too narrow, so instead of debating theories, they kept watching. Frame by frame, rotation by rotation, measuring the angles, mapping the edges. When the final full-resolution composite loaded, one detail stood out above all else. The object wasn't emitting dust the way comets do. There was no random haze, no leaking gas jets. Instead, a tight ribbon-like trail flowed behind it, coherent and stable, the kind of exhaust pattern you'd expect from a vehicle, not a rock. And still, no one in the room dared to say the word out loud. But in the eyes of every researcher, technician and observer, it was there. Design. Something about this object felt intentional, and Hubble had just caught it in its clearest light yet. When scientists first spotted the unusual brightness band in the initial Hubble images, it didn't seem significant. Bright spots are common on space objects, caused by reflective ice, surface angle, or the way sunlight hits a jagged surface. At first glance, this one seemed no different. It was situated near the upper portion of 3i Atlas's rotating mass, just left of centre, and stood out as a glaring contrast against the otherwise muted tones of the object's shell. But the anomaly wasn't in its intensity, it was in its motion. As the object rotated in the time-lapse frames stitched together from Hubble's extended imaging, researchers expected the bright zone to drift irregularly across the surface, following the chaotic wobble that most interstellar visitors show. That's how it works with natural bodies. Uneven mass distribution leads to inconsistent rotation, and bright spots shift accordingly. But 3i Atlas did something no one expected. The bright zone didn't flicker, and it didn't drift randomly. It moved in a perfect arc, across a fixed band on the surface, at a constant rate. To be precise, it moved as if sweeping. Frame after frame, the luminous region translated across the object's shell, following a curved path that stayed symmetrical with the core's rotation. It was smooth, calculated, and synchronized to a speed that matched the object's spin, not just on one pass, but over dozens of rotations. That kind of stability in a surface reflection would require either a perfectly smooth and polished material, or something actively controlling its motion. The motion wasn't just rotational, it was rhythmic. It had a cadence. Every few seconds, the band seemed to reach a reset point, then begin its journey again, like a scanner sweeping across the body. That term, scanner, was quickly adopted by the internal teams, at first jokingly, then uncomfortably, because there was no astrophysical model that could explain why a reflection would behave like that. Reflective regions on comets tend to scatter, fade, or pulse, erratically depending on the angle to the sun. But this was systematic. The reflection maintained its shape, size, and luminance, regardless of minor attitude changes in the object's positioning. It stayed true to the contour line it was bound to, and nothing, solar wind, thermal variation, or viewing angle, seemed to affect its course. One researcher suggested the possibility of a large rotating mirror-like plate, something that might be tracking the sun's position, but that opened more questions than answers. First, why would a natural object have a feature that mimics the behavior of a solar tracking satellite? Second, what material could hold that reflective quality so consistently without burning out, shattering, or degrading over time? To investigate further, Hubble's sensors locked onto the band with specialized narrowband filters. That's when the spectrum analysis returned something unusual. The wavelength of reflected light from the zone was subtly shifting, not chaotically but within a controlled frequency range, almost like a modulated pulse. In other words, the brightness wasn't just a passive reflection, it was actively varying in signal strength, like a sweeping beam with amplitude changes over time. A few analysts in the signal processing team joked it reminded them of early analog communication arrays. The orbital mechanics experts looked into whether the object might be spinning in a way that produced the sweeping effect naturally. Their conclusion was simple, not with known physics. The sweep aligned too perfectly with the object's rotational axis. If it were a natural effect, it would have to be the result of an impossibly uniform surface, one with flawless symmetry and engineered reflectivity. So what was this band? Was it a design feature? A byproduct of something operating just beneath the surface? Or was it merely a visual trick, one that just happened to imitate precision scanning with mathematical accuracy? No one could say for sure, but every scientist reviewing the data agreed on one point. It didn't look natural, and if it wasn't natural, it might be intentional. The deeper the Hubble team studied the high-resolution frames of 3i Atlas, the more strange features began to emerge, details too fine for ground-based telescopes and too symmetrical to ignore. But among all the structures that raised questions, one detail stood out immediately. It wasn't a bright anomaly or a flash or a shifting glow. It was just a line, a perfectly straight, dark line. At first, it blended into the natural contrast of the surface, appearing like a shadow or perhaps a fracture. But as the imaging rotated, the line didn't bend. It didn't distort. It remained rigid, like a ruler had been pressed against the surface of the object. It extended across a significant portion of the lower hemisphere, slightly off the rotational equator, and maintained the same trajectory across every angle. It wasn't a crack because it had no depth. It wasn't an indentation because it cast no secondary shadows. And it wasn't surface texture, because even in infrared and thermal overlays the line retained its razor-sharp form. Natural objects don't form lines like this, especially not across curved surfaces. Geology, whether on planets, moons, or comets, produces chaos, fractals, jagged, uneven fissures. But this wasn't that. This was precision. The line hugged the curvature of the object without breaking its uniformity, as if it were etched into the body by intent, not by time or collision. When scientists enhanced the section, another detail emerged. The line had identical spacing along its edges, fine markings, almost like seams, running perpendicular to its length, They weren't cracks or erosion lines, they were intervals, repeating parallel, like latches, or fasteners, or vents. That's when the comparison started pouring in. Engineers who typically worked with spacecraft imaging systems said it reminded them of access panels, segments of the hull designed to open or separate under specific conditions. Some likened it to the service seams found on satellites. Others described it as a modular join, a place where two sections of a shell might connect. But that only raised the larger question: what kind of object has join lines in deep space? Thermal scans showed something even more puzzling. The region immediately surrounding the line had a slight temperature variation, not hotter or colder, just different. A fine strip running along the seam measured a few degrees below the surrounding surface temperature. It wasn't due to shadow. The lighting angle had been accounted for. That variation suggested that the material under the line might be of a different composition, or even hollow behind the panel. That idea, hollowness, shook the core assumption of what 3i Atlas was. Comets are, by nature, dense but chaotic structures. Their mass is unevenly distributed, their cores filled with volatile ice, rock, and debris. The idea of a hollow structure, one with internal chambers or segments, doesn't match any known comet model. And yet, the presence of this line hinted at exactly that. What if this wasn't just a line? What if it was a hatch? As the object continued its slow drift toward the inner solar system, researchers began tracking the region more closely. If the line ever shifted, expanded, opened, or pulsed, it would confirm suspicions no one was ready to voice publicly. But so far the line held steady, fixed in place, unmoving, watching. A quiet rumour began to circulate among the imaging teams. If this was indeed a hatch, it hadn't opened yet, but it might. One intern even gave it a nickname: the door. Nobody laughed, because deep down everyone was thinking the same thing. There's a line on this object, and it shouldn't be there. When sunlight strikes a natural body in space, a portion of that light is reflected back into space, measurable, predictable, and consistent depending on the surface composition. Over decades of comet observations, scientists have built a catalogue of reflectivity baselines: dust, carbon compounds, frozen methane, ammonia, and various types of ice, each with its own fingerprint. So when Hubble sent back calibrated measurements of the reflected light from 3i Atlas, no one expected anything unusual. That changed the moment the numbers were processed. The surface of 3i Atlas was reflecting light at a level far beyond what should be possible for a body made of ice or rock. Not just slightly higher, significantly so. In fact, the reflectivity index exceeded even the brightest frozen carbon dioxide surfaces recorded in the solar system. It wasn't just bright. It was brilliant, almost too brilliant. At first, astronomers thought it might be an error, perhaps an artifact of overexposure or a calibration glitch in Hubble's photometric sensors, but the readings held. They repeated across multiple angles, under varying light intensities, and even with filter adjustments. No matter how the data was approached, the surface of 3i Atlas reflected light as though it were polished. And that's when the comparisons began to shift. Instead of referencing dirty snowballs and icy satellites, scientists began looking at synthetic materials, polymers, metals, even reflective alloys used in spacecraft. The surface of 3i Atlas appeared to bounce light like gold foil or titanium plating. Its spectral signature wasn't chaotic or diffused. It was smooth, uniform. The light returned in cohesive bands, as though the object was covered in panels rather than dust. The reflection had another strange quality. It wasn't uniform in every direction. Most natural objects scatter light randomly depending on topography and rotation. But 3i Atlas displayed a phenomenon known as anisotropic reflectivity, where the light bounces more strongly in a consistent direction relative to the object's axis. That's a feature typically seen in engineered surfaces, like solar sails or satellite dishes, not in interstellar rocks. Moreover, the reflectivity pattern shifted rhythmically. Every time the object completed a rotation, the bright regions would realign almost perfectly, flashing like a signal mirror at high altitude. It wasn't just bright, it was patterned, and those patterns repeated with exactitude over every spin cycle. That level of uniformity is unheard of in natural formations. researchers dug deeper into the wavelength-specific data, hoping to pinpoint the material causing such intense light return. What they found was a mystery. The spectrum didn't match water ice, carbon ice, silicates, or any frozen compound in the comet model catalogue. The reflectivity curve was too narrow, too concentrated in a tight frequency range. It mimicked something more akin to treated metal or a highly reflective coating, like multi-layer insulation used on satellites to reflect solar radiation and regulate thermal loads. If 3I Atlas were truly a comet, it would show irregular surface textures, particulate scatter, and reflection variability. None of that was present. Instead, its skin, if it could be called that, acted like a continuous reflective shell. Even stranger was the absence of glare or bloom around the brightest regions. Normally, when light hits a reflective surface in space, especially at oblique angles, it can create scatter halos or blurred fringes in telescope imagery. Not here. The return signal was sharp, clean, like a mirror returning a perfect image to the lens. This led to a chilling realization. Either the surface of 3I Atlas was composed of a material unknown to planetary science, or it had been designed to behave this way. Neither explanation fit the conventional model. So the question lingered in every observatory, whispered behind every closed-door meeting. Why does a supposed interstellar rock reflect light like a spacecraft? And what exactly is it made of? For as long as humanity has tracked comets, one behavior has remained consistent. As a comet approaches the Sun, it begins to heat up, releasing gas and dust in a process called sublimation. This creates a glowing cloud around the nucleus known as the coma, a visible shroud of expanding material driven outward by solar radiation and wind. The closer the comet gets to the Sun, the larger and more turbulent the coma becomes. So when 3I Atlas entered the inner solar system, scientists expected the same behavior. By this point in its journey, any frozen materials on or near the surface should have started evaporating violently, releasing plumes that swell the coma into a broad, radiant sphere. But that never happened. Instead, Hubble's high-resolution imagery showed something deeply abnormal. The coma of 3I Atlas remained tight, compact, and unnaturally still. At first, researchers thought it might simply be early. Perhaps sublimation hadn't begun yet, but this theory collapsed once data confirmed the object was already within the heliocentric distance where most comets erupt with visible activity. Other comets observed at this same distance had already developed massive, chaotic halos, some with expanding fans of dust jets or tails many times their own diameter. 3I Atlas, however, stayed quiet, still, as if sealed. In Hubble's images, the coma looked more like a boundary layer than a cloud, hugging the object in a thin, uniform envelope. It had no tendrils, no outbursts, no visible eruptions from the surface, and unlike other objects in solar proximity, there was no radial dispersal of dust. Instead, the thin mist remained tight and controlled, with a clean edge like a magnetic field line tracing the surface of a sphere. This led to a second theory. Perhaps the object was composed of material that doesn't sublimate. Maybe it wasn't ice after all. But that conflicted with previous observations of spectral composition, which showed signatures consistent with volatiles, at least on the outer surface. Substances like carbon monoxide and carbon dioxide should have already begun to boil off. But there was no plume, no bright jets, no erratic expansion. Then came the third possibility, one that changed the tone of discussion entirely. What if 3I Atlas wasn't simply failing to expand, but actively resisting it? What if something was containing the internal pressure, holding the volatile material beneath a shell? Scientists began to explore the idea that the object wasn't venting because its structure was sealed. A containment layer, a pressure shell, or perhaps a surface too engineered to allow sublimation to occur at all. Thermal scans added fuel to the fire. While the object was heating, the temperature gradient across the surface was unusually uniform. Typically, comets show hotspots, regions where sunlight directly strikes the surface, causing localized boiling and eruption. 3I Atlas had no hotspots. It warmed like a body with built-in heat dissipation. This kind of uniform thermal response is almost unheard of in natural objects, and is more characteristic of systems that are designed to evenly manage thermal load, just like the external surfaces of engineered probes or satellites. some scientists began comparing the coma behavior to the ion envelopes found around certain spacecraft, fields of ejected material that form structured halos without chaotic drift. But those are artificially created and managed. 3I Atlas had no known propulsion, no confirmed energy emission, and yet its coma behaved with the same restraint. To this day, no one has witnessed the object emit a traditional jet or outburst. Its halo remains sealed to its body, as if bound by intention rather than physics. It moves forward, heating without shedding mass, without surrendering to the chaos that every other visitor does. So the question deepens, is this object simply different, or is it contained? One of the lesser-known tools in a telescope's arsenal isn't just the ability to see an object, it's the ability to measure how light behaves around it. In certain conditions, when light from a star or the sun strikes a space object, some of it doesn't just reflect directly outward. It bounces. It enters surface layers, tunnels into crevices, scatters inside cavities, and eventually exits, often with a measurable delay. This is known as a light echo, and it can reveal surprising secrets about what lies beneath the surface. In the December 8th imaging sequence, Hubble's near-ultraviolet filters picked up something peculiar during a sweep across 3I Atlas's midsection. A narrow band pulse of sunlight struck the object's surface at an oblique angle, and the reflected signal did something strange. Instead of returning in a single clean reflection, it bounced twice. The second pulse came back with a delay that was not only consistent, it was measurable. That delay shouldn't have existed unless the light had entered something hollow. The first interpretation was cautious. Maybe there was a depression, a crater, a deep fold in the outer shell that created an internal bounce, but further analysis ruled that out. The delay was too precise, too sharp. It matched the kind of echo seen when light enters a smooth cavity, bounces inside, then escapes in a mirrored path. In other words, a tunnel or a chamber. What made this more startling was that the echo didn't behave like natural scatter. There was no chaos in the reflection, no diffusion. The returning signal maintained the angle of entry with near mathematical accuracy, suggesting smooth internal walls, something not found inside fractured rock or ice. And the timing between the incoming pulse and the returning echo stayed consistent over multiple rotational cycles. No matter how the object turned, the echo kept coming back with the same delay. That consistency implied the cavity wasn't temporary, it was part of the structure. As word spread among data analysts, internal messaging threads lit up with quiet speculation. Was it possible that 3I Atlas had a hollow component? A chamber within its core? Could it be a bubble in the ice formed by trapped gases, or something else, something deliberate? To rule out interference, scientists compared the echo readings with known internal cavities in solar system bodies, like lava tubes on the Moon or subsurface oceans on Europa. None of the natural comparisons matched. Those echoes return in scattered patterns because their internal geometry is rugged and broken. But the 3I Atlas echo was refined, linear, repeating. Even more unnerving, the echo only appeared on one side of the object, specifically near the same axis where the dark linear seam was discovered in Chapter 3. The possibility emerged that the two phenomena were connected, a surface hatch and beneath it an empty space. But why would a comet have an internal hollow? Nothing in the known physics of comet formation supports this. Interstellar objects should be even more chaotic than local comets, having endured millions of years of collisions, radiation and fragmentation. Yet here was 3I Atlas, bouncing light as though its insides had been carved. This echo detection forced a fundamental rethinking of the object's internal structure. It could no longer be modelled as a single solid mass. There was now strong evidence of internal architecture, or at the very least internal voids aligned with external features. Light echoes aren't just visual curiosities, they're fingerprints. They tell a story not of what something looks like, but how it's shaped inside. And in this case, that story whispered something almost impossible. This object might not just reflect light, it might be built to guide it. Cometary jets are some of the most dynamic features in astronomy. As sunlight heats a comet's surface, volatile materials inside begin to vaporize and erupt outward through cracks or weak points, forming jets of gas and dust. These jets are typically chaotic. They emerge at random angles, change direction due to spin, and flare unevenly depending on solar exposure. In short, no two are alike, and no pattern lasts long. That's why what Hubble saw on 3i Atlas stunned every scientist who reviewed the data. In the enhanced imagery from December 8th, multiple jet-like structures were visible emerging from the comet's surface. But unlike any comet previously studied, the jets weren't erupting randomly. They weren't spraying in wild arcs or changing direction with each rotation. They were geometric. The jets of 3i Atlas were arranged with symmetry. 6 visible outflows were positioned at equal intervals around the object's midsection, forming a near-perfect hexagon when mapped in 3-dimensional space. Each jet maintained its position even as the object rotated. There were no shifts, no new jets appearing at different latitudes, and no degradation in strength or angle. The structure was fixed, predictable, and precisely balanced. At first, the team at the imaging lab thought it was an illusion, a trick of shadow, or perhaps an artifact of the exposure method. But when time-lapse data was processed frame by frame, the hexagonal pattern held. The object spun, and the jet spun with it, always firing from the same nodes, always synchronized to the rotational axis. This was not comet behavior, it was closer to propulsion. In typical comets, even in the most stable ones, jets flare up unevenly as surface material is depleted. The outgassing pressure causes slight changes in spin or even sends fragments breaking off. But in this case, 3i Atlas showed no sign of instability. Its rotation remained locked, its structure undisturbed, and the jets, far from being reactive, seemed to operate with discipline. Even more telling was the spacing. When plotted using radial projection, the jet nodes followed angles of 60 degrees, exact symmetry. That degree of spacing occurs in engineered systems like nozzle arrays, ventilation modules, or stabilization devices, not in natural ice rock conglomerates. And then came the thermal overlays. Infrared imaging revealed that the base of each jet originated from a warmer region, but not too warm, just slightly elevated, consistent across all 6 sites. This uniformity was impossible to explain through sunlight alone. The sun doesn't heat separate jet vents at equal levels unless the surface is angled and shaped in very specific ways. But here the symmetry wasn't just visual, it was thermal too. Further complicating things, the material ejected from each jet wasn't drifting freely. Instead, it formed spirals, gentle, outward moving arcs that curled in the same rotational direction. The curve of each spiral matched the others perfectly, like they were choreographed. And then, finally, came the magnetic field modelling. When simulated, the outflows from 3i Atlas created a stable, centred magnetic envelope, one that shouldn't be possible from chaotic outgassing. In fact, it resembled the controlled field produced by spinning plasma systems used in certain spacecraft experiments. That's not just symmetry, that's design. Some researchers suggested the possibility of naturally formed vent channels, structural anomalies that coincidentally formed a symmetrical pattern. But no comet, asteroid, or Kuiper belt object has ever shown anything even close. 6 perfectly aligned jets, operating in sync, maintaining equal output and angle across multiple rotations. That isn't a coincidence. This wasn't chaotic eruption. This was geometric release. The kind that doesn't come from cracking ice, but from calibrated flow. The conclusion was hard to ignore. If these were jets, they weren't natural, they were intentional. To the naked eye, 3i Atlas might seem colourless, a distant glowing speck against the black of space. But under the filters of the Hubble Space Telescope, a different truth emerges. Every object in the cosmos reflects and absorbs light across a spectrum of wavelengths. And when those wavelengths are separated, enhanced and analysed, subtle colour gradients can reveal an object's temperature, composition and structure. What the December 8th images revealed was more than just a play of light. It was a signal embedded in colour. Hubble's multispectral filters produced layered views of 3i Atlas across visible, near-infrared and ultraviolet bands. The results were then mapped to false colour overlays to better visualise surface characteristics. That's when scientists noticed it, a smooth gradient, running from a pale silvery tone on one end of the object to a deep metallic blue on the other. This color gradient wasn't random. It didn't twist or swirl or break like one might expect from an unevenly heated surface. It followed a strict linear path. The transition of tones moved in a clean line along the object's longest axis, with no deviation from symmetry. It didn't pulse. It didn't shift with rotation. It held its place, locked to the same vector even as the object turned. Natural comets do not do this. Typically, color variation on comets results from chaotic exposure. Sunlit surfaces warm and brighten, while shaded regions cool and fade. The result is irregular, patchy, inconsistent. But 3i Atlas showed none of that. Instead, its surface behaved like a gradient-coated body, uniform, smooth, and deliberate. The brightest point stayed anchored to the same surface zone across every rotation, and the color transition followed what looked almost like a painted line. That's when someone on the imaging team compared it to a heat map on a machine casing. In aerospace engineering, color gradients are used to model how temperature or energy moves across a system. On satellites and probes, these transitions help identify structural stresses, power flows, or even sensor alignment. And the more they looked at the pattern on 3i Atlas, the more it resembled something manufactured. Not decorative, but functional. Even stranger was how the gradient ignored solar orientation. Regardless of the angle of sunlight, the shift from bright to dark remained anchored to the same axis. In effect, the object wasn't reacting to the sun, it was following an internal guide, a mechanical path. Spectral data revealed that the brighter end of the gradient reflected more energy in the near-infrared band, while the darker end reflected more in the blue. This could indicate thermal variance, or material variance. In either case, it meant that the surface was not a uniform blend of dust and ice. It was segmented. Deliberately or not, its coating had been divided into functional zones. The idea began to circulate that this axis, this mechanical divide, might mark more than a shift in color. It might be a conduit, a directional spine, something internal that was influencing how the surface radiated heat and scattered light. That could explain the object's stable rotation, its strange jet alignment, and even its resistance to coma expansion. What if the color gradient wasn't just a surface feature? What if it was the signature of an internal system, a circulation channel, a power source, a magnetic rail? That line, metallic silver to steel blue, didn't fade over time. It didn't blur with motion. It held its shape like a boundary on a machine, separating function from structure. For now, no one can explain it. There is no known natural process that creates color gradients with this kind of spatial discipline in a rotating interstellar object, but Hubble saw it. Clearly, repeatedly, and each time the data came in, the same line remained, straight, divided, mechanical. When an object in space rotates, its motion leaves a signature in the light it reflects. As different parts of the surface move toward or away from the observer, wavelengths stretch or compress in predictable ways. This phenomenon, Doppler drift, is a cornerstone of astrophysical measurement. It tells us how fast something spins, how unevenly mass is distributed, and whether the rotation is stable or chaotic. For 3i Atlas, the Doppler data from December 8th didn't just offer measurements, it offered a revelation. As Hubble tracked the object over multiple rotations, the spectral data returned with extraordinary clarity. The wavelengths shifted exactly where expected. One side of the object showed a slight compression of light as it moved toward the telescope, while the opposite side showed expansion as it moved away. That was normal. What wasn't normal was everything else. In natural bodies, the drift pattern wobbles. Comets tumble, asteroids shake, and even large moons exhibit subtle, irregular variations caused by uneven internal mass. But 3i Atlas displayed none of that. The Doppler pattern didn't wobble even slightly. Each cycle was identical to the one before it, down to the smallest measurable detail. The object rotated with the kind of stability seen only in engineered systems. It spun like a gyroscope. There was no precession, no tilt, no drift, no gradual shifting of the rotation axis over time. For an interstellar object travelling through multiple gravitational fields, this was nearly impossible. Natural bodies get nudged, pulled, torqued, and disturbed as they move. Yet 3i Atlas behaved like something actively maintaining its orientation. Scientists began to test the data from every angle. They filtered out thermal noise. They checked for solar wind interference. They compared multiple wavelengths to ensure the results weren't the product of instrument distortion. But no matter how many times they recalibrated or reprocessed the readings, the outcome stayed the same. The rotation of 3i Atlas was controlled. Not stable by chance, not balanced by coincidence, controlled. The amplitude of the Doppler drift told another story. The object wasn't spinning quickly. In fact, its rotation was remarkably calm. Too calm. Most comets pick up rotational speed as they approach the Sun and begin shedding mass. Jets erupt unevenly, pushing the body into a chaotic spin that eventually stabilizes only after large amounts of material have been lost. But 3i Atlas wasn't shedding anything. There was no coma expansion, no mass ejection, no instability. The absence of wobble suggested that its mass distribution was nearly perfect. Either it was extraordinarily dense and smooth, or its internal structure was arranged with symmetry so precise that no forces could disturb it. That level of balance isn't found in nature, it's designed. The Doppler drift also revealed that the object compensated for solar torque, something natural bodies don't do. As the Sun's radiation pushed against one side, the rotation didn't accelerate or slow. It held its speed with uncanny consistency, as though some internal mechanism corrected for external force. Another anomaly emerged when scientists mapped the drift over each jet region described earlier. The jets didn't affect rotation at all. If they were natural outgassing vents, they should have nudged the object, altering its spin rate even slightly, but nothing changed. The jets aligned with the rotation, not the other way around. It was as if they were placed intentionally to maintain the object's rotational symmetry. By late afternoon, Doppler specialists began comparing the rotational behavior to that of spinning satellites, specifically those equipped with momentum wheels or magnetic stabilization systems. These devices allow spacecraft to maintain orientation in deep space without needing constant thrust. 3i Atlas behaved exactly like one of them. Whether by physics or intention, the spin of 3i Atlas didn't match anything in the catalogue of natural objects. It didn't sway, it didn't drift, it didn't react, it held, and that level of control suggests one thing above all else. Something, inside or on the surface, is governing its rotation. One of the first tasks scientists undertake when a new object enters the solar system is to chart its path, both forward and backward. The forward projection tells us where it's going. The backward projection tells us where it came from. For 3i Atlas, those calculations began immediately after its discovery. The object's speed, angle of approach, and apparent trajectory through the outer regions suggested it had come from beyond our solar system. That alone made it historic. But with the new high-resolution Hubble data from December 8th, researchers expected to finally confirm which part of interstellar space 3i Atlas came from. They had the tools, the models, and most importantly the clarity. For a brief moment, the team believed they were about to pinpoint the exact region in the galaxy from which this object had originated. That hope didn't last long. Using the updated trajectory data, scientists ran orbital simulations to project the object's path backward through space. The models took into account every major gravitational influence: our Sun, the outer planets, even interstellar drift. The results were clean, precise, but also impossible. No known star system matched the inbound path. The object had entered the solar system on a trajectory that defied all the usual gravitational fingerprints. There was no slingshot curve, no perturbation from nearby stars, no fading echo of a distant solar escape. The line traced back into open space, empty space, the kind of space with nothing in it for tens of thousands of years of travel time. At first, researchers assumed the data might be incomplete. Perhaps a passing star had nudged it, altering its path, or maybe an earlier gravitational interaction had thrown it off course. But when they pushed the models back further, hoping to find that missing link, something stranger happened. The trajectory didn't fade, it fragmented. After a certain point in the simulation, the object's past velocity began to contradict known physics. Instead of gradually slowing as it moved away from our system, the object seemed to speed up in reverse time. The math reversed itself. This wasn't an error in software. It was a failure of the model to reconcile what should have been a continuous path. It was as if 3i Atlas hadn't fallen into the solar system. It had appeared on course. This idea sent shockwaves through the astronomical modelling community. If the object had no discernible past, no definable origin, then the standard categories no longer applied. It wasn't just an interstellar visitor, it was a trajectory anomaly. To check for alternatives, scientists compared the path to two other known interstellar objects, Oumuamua and 2I Borisov. Both had inbound trajectories that loosely aligned with stellar systems or galactic drift patterns. Their origins weren't crystal clear, but they fit within expectations. 3I Atlas did not. Its vector was tighter, cleaner, too clean. Further compounding the mystery, simulations revealed that the object's current path is remarkably fine-tuned. It entered the solar system at just the right angle to avoid planetary capture, but still allowed multiple observation windows. It didn't clip Jupiter, didn't skim Neptune, didn't vanish past the Kuiper belt. It threaded a needle, and did so with what looked like intention. Several theorists began quietly asking a question they never thought they'd entertain. What if this isn't just an object travelling through space? What if this object was sent? Because if it had no origin and no chaotic motion, and if its path doesn't match natural gravitational evolution, then maybe it's not the result of chance. Maybe it's the result of choice. And for now, the only thing every model agrees on is this. 3I Atlas didn't come from anywhere we recognise. Its origin has been rejected, and that's the most unsettling answer of all. Every time a space object passes between us and distant stars, it creates a visual opportunity, a test of transparency. Even when the object itself appears opaque to the eye, starlight often filters through dust clouds, comet tails, or gas layers, revealing clues about composition and density. For decades, astronomers have studied this faint background transmission to understand the nature of objects too far away to touch. When Hubble pointed its sensors at 3I Atlas on December 8th, part of the goal was simple: capture light from distant stars as it passed through or around the object's tail. With the object moving into a prime alignment zone, it was the perfect chance to analyse its halo, its core, and everything in between. But what should have been a textbook observation turned into something nobody could explain. There was no light, not less light, not diffused light, no light at all. Every star that should have been visible behind the object simply vanished as 3I Atlas passed in front of it. In normal comet observations, background starlight softens but doesn't disappear. Even the densest tails let photons leak through in thin bands. But in this case, the object blocked everything, cleanly, sharply, and completely. It was as if someone had cut a hole out of the background. At first, scientists assumed it was an image saturation issue. Perhaps the brightness of the object overwhelmed the telescope's sensors and drowned out the faint background points. But this didn't hold up. The exposures were balanced, carefully layered in separate filter bands and calibrated for high contrast. The stars reappeared the moment 3I Atlas drifted out of frame. They were never missing, only perfectly blocked. Next came the idea that perhaps the coma, the hazy envelope surrounding the object, was denser than expected. That would be unusual, but not impossible. Still, the coma didn't behave like a dense cloud. It showed no signs of absorption, no gradation in transparency, and no colour filtering effects. It wasn't acting like gas at all. It was acting like a shell. But comets don't have shells. Digging deeper, the analysis team began charting the edges of the blackout zone. They expected to find a gradient, a fuzzy transition where starlight would bend or scatter at the object's perimeter. What they found instead was shocking. The transition was abrupt, pixel sharp. The moment a star entered the boundary region, it disappeared. The moment it exited, it returned. No blur, no distortion, just a binary state, light on, then gone. This behaviour suggested one thing above all. 3I Atlas wasn't just dense, it was impenetrable. That level of optical blocking implies extreme structural consistency on the level of metals, alloys, or artificially layered composites. Nothing natural in deep space has that kind of uniform density. Even the thickest asteroids contain porous interiors. Even the most solid moons allow seismic transmission. But this object, it might as well be solid black glass. Worse, the opacity wasn't limited to visible light. Infrared scans from the James Webb Space Telescope, coordinated with Hubble's December 8th pass, also reported near-total blockage. Normally, even a dense object will glow faintly in the infrared due to thermal radiation. But Webb's sensors picked up an unusual dip in emissions. It wasn't cold, it wasn't hot, it was absent, like the object was swallowing the signal. This absence of background light pushed some teams to propose shielding behavior, maybe some kind of field effect or an outer layer that deflects electromagnetic energy. These ideas would have been dismissed just a few months earlier, but now, with symmetry, jets, internal echoes, and structured rotation already confirmed, nothing seemed too far to consider. The conclusion wasn't immediate, it crept in slowly, as each team confirmed the same eerie result. You can't see through 3i Atlas. Not optically, not thermally, not at all. Whatever it's made of, it isn't letting anything in, or out. In the study of rotating celestial bodies, the poles often tell a deeper story. Whether it's the magnetic poles of a planet or the rotational axis of a comet, these regions usually reveal dynamic interactions. Jets erupting from surface cracks, temperature anomalies from uneven spin, or radiation leakage through structural gaps. The polar axis isn't just a reference point, it's often the place where symmetry breaks and nature shows its hand. But on December 8th, when Hubble captured 3i Atlas in unprecedented detail, scientists noticed something deeply abnormal about its poles, or more specifically, about what was not there. Nothing. No emissions, no jets, no light, no heat, just stillness. When filtered through near-ultraviolet and thermal sensors, the area along the object's rotational pole, particularly the northern axis, registered blank. It wasn't cold in the traditional sense, it wasn't dim, it was silent, like a void. This silence wasn't consistent with natural bodies. Comets typically show turbulence at their poles. As the object rotates and solar energy hits the sides unevenly, the poles often become stress points. Cracks form, gases escape. Even when inactive, they reflect faint light or thermal signatures from the surrounding material. But here, with 3i Atlas, the pole wasn't dim, it was non-responsive. The surrounding surface reflected light normally. The coma behaved as expected around the equator, but the pole remained untouched. It didn't reflect, it didn't absorb, it didn't re-emit. It simply existed as a perfectly black corridor in every measurable band. At first, researchers thought this could be a shadowing issue. Maybe the lighting angle during the observation happened to cast the pole into darkness, but orbital models ruled that out. The sun was striking the object at a glancing angle, and the polar region should have been partially illuminated. Even in total shadow, infrared would still detect residual warmth, but there was none. The Webb Space Telescope confirmed it. In the thermal range, the pole was a blind spot, absorbing or deflecting every wavelength thrown at it, like a lens cap covering an observation port. Some began to wonder, was this truly a physical absence of signal, or the presence of something blocking it? Analysis teams ran simulations using various materials, carbon-rich dust, fractured regolith, porous rock, but nothing matched the measured silence. Then they tried modelled materials from aerospace applications, radar-absorbent coatings, stealth-grade polymers, thermal insulating composites. Only then did the absence make sense. But those substances don't occur naturally. Which raised the question, why would only the pole be shielded? The symmetry of the object had already defied expectations. Its jets were geometrically aligned, its shell was smooth and highly reflective, but the pole seemed hidden on purpose, like a hatch sealed tight, or a port that hasn't opened. And there was one more twist. Every single Doppler and magnetic reading, every scan of the object's rotation and axial field showed no irregularity, no axis shift, no magnetic asymmetry, except, along that same polar corridor, magnetometers picked up a dead zone. The field lines around the object bent, but only near the pole, as if something was redirecting them. This wasn't just a blank spot, it was controlled absence. Theorists began referring to the axis as a null window, a place on the object where emission was not just missing, but actively prevented. No heat, no light, no magnetism, no signal reflection. The deeper question became not just what was being blocked, but why that part of the object would need to be so completely sealed. Was it a relic, a buried system, a propulsion aperture, or something far more advanced, something that only opens when the timing is right? We don't know. We've never seen anything like it. What we do know is this. The polar axis of 3i Atlas is quiet. too quiet. And in the language of space, silence is never just silence. One of the most predictable features of a comet is its tail, and more specifically, the direction that tail takes as it interacts with the Sun. Whether composed of dust or ionized gas, a comet's tail is always shaped by the solar wind, streams of charged particles blowing outward from the Sun at immense speed. The physics is simple. The tail should always stretch away from the Sun, like a windsock in a cosmic breeze. But with 3i Atlas, the tail doesn't follow the rules. In fact, it defies them completely. When Hubble captured full-length exposures of the object on December 8th, scientists expected to see a long, sunward curved stream trailing behind the nucleus. Instead, what they saw was a tail that bent in an impossible direction, curling nearly 90 degrees off its expected axis, not drifting, not fluttering, bending deliberately, like a rigid structure being steered. At first, the team assumed this was an observational distortion. Perhaps the camera angle had exaggerated the curvature, or the apparent direction was skewed by parallax. But when confirmed across 3 independent observatories, and later by the James Webb Space Telescope, it became clear. The tail of 3i Atlas was not behaving like a tail at all. Instead of reacting passively to solar wind pressure, it appeared to be moving along a defined vector, with structural consistency. The curve was smooth, symmetrical, and, most alarmingly, maintained even as the object changed orientation. To understand how strange this is, imagine a flag mounted to a pole on a moving car. No matter how the car turns, the flag should always stream in the direction opposite the motion, reacting to airflow. But in the case of 3i Atlas, it's as if the flag remains locked to the side of the car, bending only as if guided by an unseen hand. This forced scientists to consider more exotic possibilities. Was the tail interacting with a hidden magnetic field? That would be unusual, but not unheard of. Ion tails from some comets have been known to temporarily respond to solar magnetic field lines, but never like this. Never with such permanence and precision, and most importantly, never with curvature that stays stable across days of observation. Spectral imaging revealed another oddity. The composition of the tail didn't resemble that of a standard dust or gas tail. It lacked the diffuse scattering typical of ice grains and carbon particulates. Instead, it appeared more tightly bound, like a plasma filament. And yet even this didn't explain the shape. Plasma responds to magnetic fields, but this tail didn't behave like a passive plasma stream. It bent too cleanly, too predictably. Then came the simulations. When researchers fed all available parameters into fluid dynamics software, gravity, solar pressure, heliocentric motion, the tail model refused to match the images. The only way to recreate the shape was to introduce an external force, not from the Sun, not from another body, but from within the object itself. This suggested an unthinkable possibility. 3i Atlas might be steering its own tail. If true, that would imply control over mass ejection, possibly through directional jets, electromagnetic shaping, or structural geometry engineered to manipulate its own exhaust path. But even that explanation only scratches the surface. The question remains, why would an object want to guide its tail? In natural systems, the tail is a byproduct. But in engineered systems, rockets, satellites, even propulsion prototypes, trails are often controlled for trajectory correction, stability, or even communication. Could the tail of 3i Atlas serve a function beyond dispersion? Was it radiating something? Signaling? Masking something else? Nobody can say for sure. But the one thing everyone agrees on is this. That tail shouldn't bend like that. Not without help, not without purpose. When an object spins in space, the light it reflects often changes depending on surface texture, composition, and the angle of sunlight. This shifting brightness is common. Comets pulse as icy patches reflect light more strongly, and asteroids flicker like lighthouses as jagged surfaces catch solar rays at just the right moment. But these fluctuations are usually messy, irregular, driven by chaos and randomness, not with 3i Atlas. The object didn't just flash, it pulsed, with rhythm, with timing, and it did so with such unwavering regularity that it no longer resembled natural behaviour at all. On December 8th, as Hubble tracked 3i Atlas across its full rotational cycle, something remarkable emerged in the light curve data. Every time the object completed a rotation, a distinct spike in brightness occurred, sharp, consistent, and perfectly aligned to the same point in the spin. Then, as the object rotated on, the brightness dipped again. Not gradually, not in a soft fade. It dropped with discipline, as though someone had flicked a switch. That spike repeated exactly once per revolution. At first, the brightness changes were subtle, only noticeable under tightly focused photometric filters. But when the data was smoothed and charted across multiple revolutions, the pattern sharpened into a clean waveform, and more importantly, it did not drift. Over dozens of observed rotations, the pulse returned at the exact same angle, at the exact same time interval. It did not shift forward. It did not lag behind. This behavior, known as synchronous reflectivity, is something we rarely see in natural bodies. In fact, it's more commonly associated with rotating satellites that have reflective components, such as solar panels, radiator fins, or sensor arrays. These structures catch and reflect light at specific points in their rotation, creating predictable brightness flares. But those are machines, built with precision. 3I Atlas was supposed to be a comet, so why was it behaving like a satellite? Spectral analysis of the bright zone revealed more surprises. The reflected light was unusually narrow in wavelength, suggesting a highly uniform surface, possibly metallic or coated with engineered material. Natural surfaces reflect a broad spectrum, with diffuse edges. This was different. The light spike was laser sharp, like it was bouncing off a polished surface or mirror. Even stranger, the brightness didn't vary in strength from rotation to rotation. It stayed steady, as though the same patch of surface, whatever it was, hadn't degraded, shifted, or altered in any way. That level of consistency over time implies structural permanence and possibly design. This led scientists to model the object's surface as a rotating polyhedron, with one facet acting as the reflective zone. But simulations showed that the spike was too precise to come from an uneven rock. The rotation would need to be tightly controlled, with no wobble and no mass irregularities, which, according to prior Doppler drift data, it was. What emerged was the picture of a structure that not only spun with balance but also flashed with intent. The reflection acted like a signal, brief, exact, and repeated. Some even suggested that the pulse could be used as a beacon, visible across millions of kilometers, announcing its presence to any observers capable of reading the rhythm. Was it a coincidence? A natural body just happening to reflect sunlight in perfect sync with its spin? Or was this object broadcasting its location, repeating a signature like a cosmic heartbeat? In deep space, light is often the only language that travels far. And 3I Atlas was speaking in time, over and over again, one revolution, one flash, again and again, like a lighthouse with no coast, or a probe with no home. In astronomy, fine surface features are often the last to be detected, and the most revealing. Large telescopes like Hubble can resolve planetary storms, polar caps, even impact scars on distant moons. But when it comes to interstellar objects, getting a clear view of surface texture is rare. Most pass too far, too fast, and with too much noise to capture precision detail. But 3I Atlas, on December 8th, gave us a glimpse at something else. Using Hubble's high-contrast edge enhancement tools, analysts zoomed in on a curved segment near the object's trailing rim, where sunlight grazed the surface at a low angle. What emerged wasn't a crater, it wasn't erosion, it wasn't random cracking, it was uniformity. A row of parallel grooves etched cleanly into the surface, deep enough to cast shadows, sharp enough to resist being called natural. At first glance they resembled geological striations, like the grooves left behind by glacial activity on Earth. But comets don't have glaciers, and they don't create straight, evenly spaced lines that match each other in width and depth. Not like this. These weren't scratches, they were cuts. What struck researchers most was how the lines followed the curvature of the rim with mathematical precision. Each indentation mirrored the angle of the last, the spacing nearly exact. Measured edge to edge, the distance between the grooves was consistent within a margin of error far too tight for nature. Some compared it to ribbing, reinforced structural scoring seen on aerospace materials to strengthen hulls under stress. The suggestion was subtle but haunting. These weren't flaws in the surface. They were features. The Hubble team ran light-shadow simulations to test whether the grooves could be artifacts, false patterns created by imaging resolution, or pixel sharpening. But in every model, the shadows cast by the indents remained real. As the object rotated, the angle of sunlight shifted, and each groove reacted exactly as a three-dimensional recess would. These weren't flat textures, they had depth. This depth presented another problem. Natural surface grooves, even in the cleanest rock formations, show variation. They twist, they widen, they taper. These grooves didn't. They ended suddenly at the same depth, like they'd been carved by a machine that knew when to stop. Some suggested the possibility of a fragmentation event, that perhaps long ago the object had broken off from a larger structure, and the grooves were scars from separation. But that raised an even more uncomfortable idea. If it was a fragment, what kind of object had it separated from? Infrared imaging showed that these grooves were slightly cooler than the surrounding surface. That could mean they were deeper, shielded from the sun, or made of a different material. Perhaps even openings for something yet to emerge. Theories began to branch in two directions. One camp proposed a passive explanation, that the grooves were remnants of unknown interstellar geological forces, extreme magnetic fields, unknown material behaviors, something exotic but still natural. The other camp saw it differently. To them, these grooves resembled access panels, heat radiators, or even stabilizing fins from a buried structure. But both sides agreed on one thing. No previous interstellar object had ever displayed anything remotely similar. And if you stood back and looked at it, zoomed out from the math, the filters, the charts, one thing became clear. It didn't look broken. It didn't look ancient. It looked designed. Not just a rock spinning through the void, but a surface waiting to reveal its next layer. A shell with edges and a rim that had been cut. In the realm of deep space observation, timing is everything. Not just in trajectory or spin, but in how light and energy behave as they interact with an object's surface and what lies beneath. With powerful instruments like Hubble and the James Webb Space Telescope, scientists can detect even the faintest delays in light return. These delays, often measured in milliseconds, are called light echoes. They serve as an indirect form of sonar in space, bouncing photons off a target and interpreting the gaps in response to understand internal structure. On December 8th, as Hubble's imaging focused tighter on the midsection of 3I Atlas, analysts noticed something odd. The light echoes weren't coming back evenly. They were slowing down, specifically as they approached the object's core. Initially, the outer shell returned light normally. The pulses, even at oblique angles, followed a clean, predictable delay curve. But deeper into the body, especially near the geometric center, the delay expanded. Not dramatically, but enough to catch the attention of the modeling teams. It wasn't a glitch. It wasn't noise. The echo was bouncing deeper and taking longer to come back. That kind of delay only means one thing: internal complexity. In natural bodies, echo delays usually signal porous structure, like honeycombed ice or fractured rock. But those delays tend to be random, uneven. Reflected light gets scattered by irregular cavities, making it noisy and imprecise. In contrast, the delays in 3I Atlas were clean, layered. They followed a pattern of increasing intervals, suggesting the light was moving through discrete zones, like chambers, like levels. To test this, scientists ran simulations using concentric shell models, hollow interiors surrounded by denser outer layers. The results lined up shockingly well. The echo data mimicked what you'd expect if light was travelling into a nested series of internal walls. Not porous rubble, but structured layers. The implications were staggering. A hollow comet is rare. A comet with organised internal architecture is, by all current scientific definitions, impossible. But the data didn't lie, and the shape of the delay curve told another story. The deeper the light travelled, the more stable the echo became. Instead of scattering wildly, it returned with precision, almost like bouncing off flat reflective surfaces arranged in geometric intervals. That kind of internal response doesn't happen in randomly formed matter. It happens in engineered materials, cavities carved with purpose. Even more unsettling was the shape of the core's return signature. Instead of the chaotic diffusion expected from shattered rock or pressurized ice, The central pulse came back as a soft round wave, like a dome. It was smooth, gentle, as if the centre of 3i Atlas wasn't fractured but protected, as if it was the quietest, most shielded part of the entire structure. That protection suggested pressure boundaries, containment, possibly even insulation. And if true, that would mean 3i Atlas wasn't just hollow. It was built to keep something inside. Was it storing energy, protecting fragile systems? Or worse, was it waiting, infrared and microwave? Overlays provided further clues. Heat flow around the central delay zone was minimal, indicating that it wasn't just hollow, but possibly shielded thermally as well. There was no radiant hotspot, no reactive core, just silence, wrapped in layers of increasing resistance. The term used quietly by one analyst was core nesting, a concept pulled not from comet theory, but from aerospace design, where sensitive instruments are protected by multiple shells to dampen outside force. That term, core nesting, stuck, because it described something that no one wanted to say out loud. 3. Atlas might not just be a hollow shell, it might be compartmentalized, built from the inside out. And as light continues to enter its core, the delays only grow longer, as if we're chasing something down a corridor that never ends. Every known comet, asteroid, or interstellar visitor shares one trait in common: chaos. These objects are ancient, bruised by time, and shaped by 1,000,000 years of collisions, heating, and decay. As they drift through the void, they leave trails of debris, fractured rocks, ice shards, and vaporized dust. Even the most structurally sound objects shed particles, especially as they approach the Sun. Gravity alone ensures that no object travels perfectly clean. But 3i Atlas doesn't follow that rule. When Hubble tracked the object on December 8th, part of the mission was to study its surrounding environment, analysing the immediate space around it for signs of activity, mass loss, or fragmentation. To everyone's surprise, that space was empty. Not just sparse, completely clean. There was no visible debris field, no orbiting fragments, no trailing material beyond its core and unusually compact coma. Across multiple spectral bands, from visible light to deep infrared, the area around 3i Atlas showed nothing. No echoes, no shadows, no reflections. The object travelled like a sealed vessel, not a weathered rock. That silence raised red flags. Comets are not silent travellers. As they near the Sun, their surfaces heat and eject volatile material, creating clouds of microscopic particles. These particles form tails, halos, and secondary trails. Even comets that haven't approached the Sun for millennia still carry scar tissue, fragments orbiting in a loose cloud, evidence of past collisions or outgassing events. Yet with 3i Atlas, none of that was present. This absence wasn't just visual, it extended into other detection channels. Radio telescopes found no Doppler reflections from stray material. Thermal arrays picked up no warm particles in the object's wake. LiDAR mapping systems, which are capable of detecting even centimetre-scale objects in orbit, found nothing. The area around 3i Atlas was blank. It was as if the object had scrubbed its path clean. Some researchers proposed that the debris field had already dissipated, lost to time, scattered by solar wind. But simulations showed that debris from even minor mass loss events can linger for weeks, especially in the vacuum of space. Others suggested that the object had never fragmented. But even if that were true, micrometeor impacts and cosmic radiation should have eroded its surface over time, releasing at least some particulate matter into orbit. So why was there no evidence of any damage? The object looked pristine. Theories began to form around the idea of shielding. What if the material on the surface wasn't just strong but actively protective? Some even floated the possibility that the surface self-sealed, that instead of breaking apart it absorbed or redirected energy. Then came the idea no one wanted to say too loudly. What if the object was designed to leave no trace? In aerospace design, certain vehicles, especially probes or stealth systems, are built to minimize debris. They operate with containment protocols, ensuring no uncontrolled fragments escape during operation. Could 3i Atlas be exhibiting the same behavior? Could this be evidence of an internal system regulating its emissions, actively maintaining a zero-loss trajectory? Other anomalies supported this idea. Its jets were symmetrical. Its rotation was perfectly balanced, its coma didn't expand under heat, and now even its trail was clean. That left one final chilling conclusion. 3I Atlas was either the most stable natural object ever observed, or it was maintaining itself, repairing, sealing, containing, and that made scientists ask, why? What kind of object moves through space with zero friction, zero fracture, and zero fallout? One answer is terrifying in its simplicity, something that was meant to arrive intact, and as of now, nothing, not even dust, has broken free from its skin. Whatever it is, it's not crumbling, it's whole, untouched, and still coming. When light interacts with space objects, the edges often tell a deeper story. The rims of asteroids flicker with uneven shadows. The silhouettes of comets shift and blur under changing solar angles. But with 3I Atlas, the edge didn't just glow. It formed something no one expected, a perfect arc. On the morning of December the 8th, as Hubble captured the object from a slightly offset angle, a soft band of light appeared along the outer rim of 3I Atlas's leading edge. At first, scientists assumed it was standard backscatter, sunlight grazing the surface and refracting off dust particles or rough texture. But as the frames continued to arrive and the object rotated, the band of light remained, unwavering, symmetrical, and unbroken. It didn't behave like a flare. It behaved like a boundary. The glow curved around the visible silhouette in a seamless contour, forming a continuous luminous arc that extended nearly 1/3 around the object's perimeter. Not just in one image, but in every frame of the full rotation cycle. It didn't change thickness. It didn't pulse. It simply existed, stable, like a halo frozen in motion. Scientists tested the usual suspects. Was this diffraction, lens flare, an angle-related trick from Hubble's optics? But those phenomena distort with motion. This glow did not. When the object rolled, the arc moved with it, always clinging to the same relative position on the body, never breaking formation. What made it stranger was the intensity. The glow wasn't random or diffused. It peaked precisely at the midpoint of the arc, then faded evenly toward both ends. That symmetry ruled out natural irregularities. It was emitting, or refracting, with the kind of controlled gradient seen only in engineered light patterns. To verify its authenticity, spectral overlays were run. The arc emitted strongly in near-ultraviolet, suggesting high-energy photon interaction at the boundary. But there was no source, no heat spike, no vent, no radiation leak. The glow wasn't coming from within the object. It was being generated at the edge. This led to an unnerving theory. The arc wasn't just light, it was a field. In particle physics, edge glow emissions like this are sometimes observed when charged particles interact with structured magnetic boundaries, such as the ionosphere around Earth, or the containment fields used in fusion experiments. These arcs appear smooth, self-contained, and follow predictable geometry. They are a byproduct of control, not chaos. Could 3I Atlas be exhibiting similar behavior? When scientists modeled a low-intensity electromagnetic sheath wrapping the object's exterior, the data lined up almost too perfectly. The glow followed the curvature of what would be a stable, low-frequency field, something that could serve as a protective layer or even as a containment zone. But comets don't generate fields. They don't emit arcs. They don't have edge-defined boundaries that behave like energy membranes. And yet, 3I Atlas did. Some speculated that the glow might be a passive reaction, sunlight activating a unique material coating. But this raised more questions than it answered. What kind of material could produce that level of consistency? What surface could refract light with such discipline over a constantly rotating object? Others began comparing the arc to limb-brightening effects seen around artificial satellites when exposed to extreme solar conditions. But this only deepened the mystery, because to show limb brightening, a structure needs to have curvature, coating, and controlled interaction, all signs of artificiality. So what exactly is this arc? A shield? A propulsion envelope? Or the visual trace of something far more advanced? We don't know yet. But what we do know is this. This isn't the reflection of a rough rock. It's the perimeter signature of something intact, something whole, and possibly active. In the cold darkness of deep space, arcs like this don't just appear. They're formed, or projected, And as of December 8th, we're not looking at shadows anymore. We're looking at boundaries. The Hubble Space Telescope has operated continuously for over 3 decades, orbiting Earth with an impeccable track record of stability and precision. Its instruments have captured everything from the faint light of ancient galaxies to the icy plumes of outer moons. And while occasional calibration issues are expected in any long-term mission, unexplained glitches, especially during critical observations, are rare. But during the imaging run of 3i Atlas on the morning of December 8th, something happened. For just under 4 seconds, 2 of Hubble's imaging sensors fell out of sync. At first, no alarms were triggered. The drop occurred in a silent window of passive data collection. No instrument failure, no heat spike, no reported power dip. The main science computers flagged a temporary desynchronization between the Wide-Field Camera 3 and the Fine Guidance Sensor. Normally these systems align precisely, with nanosecond accuracy, to stabilize image resolution. But in this case, a split-second misalignment resulted in a slight image blur. So small it almost went unnoticed. Then it happened again. Exactly 34 minutes later, during another sweep across the object's equatorial region, the same 2 instruments desynced, this time for nearly 7 seconds. The onboard system corrected the error, restored alignment, and resynced the image feed. But this time, internal logs recorded a more unusual note. Signal interference. Not from solar radiation, not from Earth's magnetosphere, from within the field of view. It didn't take long for system engineers to notice the correlation. Both glitches occurred when 3i Atlas was in near-center frame. Both times the affected sensors were focused near the same region of the object, specifically just above the strange arc glow observed in Chapter 18. This wasn't a malfunction, it was a disruption. The team conducted diagnostics. They ruled out heat distortion, cosmic ray strikes, onboard software faults, and solar interference. None matched the signature of what was recorded, and crucially, no other telescope observing the same sector experienced any sensor faults. Only Hubble, only during its close examination of 3i Atlas. What's even more strange is what happened between the glitches. Telemetry logs from the affected instruments show a brief moment of data overwrite. Not total loss, just noise. A burst of meaningless data injected into the buffer for a duration too short to corrupt the feed, but long enough to be detected. In the world of deep space imaging, even milliseconds matter. And this noise wasn't random. It had structure. The signal resembled known interference patterns caused by proximity to high-frequency emitters, devices that pulse low-power waves across short distances. In Earth orbit, such glitches can occur when satellites pass through communications beams. But in deep space, there are no satellites nearby. Nothing artificial, nothing human, unless something in the frame wasn't natural. That possibility triggered a quiet protocol. The logs were reviewed, re-reviewed, and eventually sent to 2 external analysis teams, one specializing in signal contamination, the other in passive electromagnetic field detection. Their conclusion, while cautious, was unsettling. The sensor glitch was consistent with low-level field interference, like that produced by a localized electromagnetic envelope, which means this: 3i Atlas may have emitted something, not a radio burst, not a visible pulse, something quieter, something shielded, a whisper in the spectrum that didn't broadcast, but disrupted. Why would a comet interfere with the world's most stable telescope? Why would that interference happen twice, in the exact same way when the lens was fixed on a single region of its surface? And perhaps most disturbing of all, what else didn't Hubble see during those lost seconds? Because for just a moment, one of humanity's clearest windows into space blinked, and whatever caused that blink was not dust, was not debris, and was not random. It was timed, it was localized, and it was silent. As comets and other celestial objects approach the sun, they almost always begin to spin faster. It's a simple, well-documented physical response to heating and mass loss. Gases trapped beneath the surface begin to vaporize, jets erupt unevenly from fissures, and like miniature thrusters, those eruptions apply torque. Over time, this causes a gradual acceleration in rotation, sometimes enough to destabilize the object entirely. 3e Atlas, by all accounts, should have been doing the same, but it wasn't. Since the earliest observations of its trajectory, Scientists have tracked the object's rotational period with precision. Using Doppler drift, light curves, and brightness pulsation intervals, they charted its spin down to the second. As of late November, the object was spinning steadily, once every several hours with no noticeable wobble or drift. Then, on December 8th, Hubble delivered something strange. Nothing had changed. After weeks of increasing solar proximity, with rising surface temperatures and mounting solar wind pressure, 3i Atlas should have been spinning faster. But the object's rotation remained exactly the same. Same speed, same axis, same balance. At first, this seemed like good news. A stable spin means better observational data, easier modelling, and fewer variables. But beneath the surface, it triggered alarm. Because it wasn't just unlikely, it was physically improbable. The object had jets. That was already confirmed. 6 symmetrical streams of outflowing material observed through both Hubble and ground-based telescopes. Even with perfect symmetry, the smallest imbalance should have begun to influence the spin, but no such influence existed. The jets weren't nudging it at all. It was as if the object resisted being spun. That's not what nature does. That's what systems do. One hypothesis was internal mass distribution. Perhaps the object was so dense and uniform that it absorbed and redistributed every force evenly. But that would require a level of material engineering unheard of in natural objects, especially something supposedly formed in deep interstellar space. Another possibility was that the jets weren't real jets at all. Maybe what appeared to be outgassing was actually electromagnetic in nature, visual but massless. But spectroscopy had already confirmed some form of material ejection, even if minimal. So why wasn't it changing the spin? Researchers turned to high-resolution time-lapse imaging. They aligned dozens of full rotation cycles across multiple wavelengths, hoping to catch any slight shift, a fraction of a second, a lean, a lag. But there was nothing. 3i Atlas rotated with the kind of consistency seen in Earth-orbiting satellites, those equipped with reaction wheels, spin regulators, or magnetic torque rods. Objects designed to maintain their orientation no matter what they encounter. The comparison wasn't lost on the scientific community. To maintain a constant spin under changing external pressure, an object needs either active stabilization or passive resistance. Either it's adjusting in real time with internal mechanisms, or it was built so perfectly that it doesn't need to. Both explanations point to the same uncomfortable truth. This object was built to stay stable. There's also a deeper implication. Without acceleration, the object avoids a catastrophic fate common to natural comets, spin-induced disintegration. As comets speed up, the centrifugal force can rip them apart. 3i Atlas wasn't just spinning steadily, it was preserving itself. As the data rolled in, one analyst wrote a quiet note in the margin of the light curve graph. Refuses to spin faster. Why? Holding position? That question echoed through internal meetings for days, because if the object wants to stay at a fixed speed, if it's actively holding itself there, then maybe it's waiting for something, or aligning with something, or responding to a schedule we can't yet see. All we know is this. 3i Atlas is not behaving like a drifting piece of ice. It's behaving like something with purpose, something with resistance, something with control. In the vast, unshielded environment of deep space, impact craters are inevitable. Over time, every asteroid, comet, and planetary moon becomes scarred with the evidence of countless collisions. Tiny meteoroids, dust impacts, and high-speed fragments leave behind dimples, pits, and gouges. These marks are the fingerprints of the cosmos, and they tell the story of an object's age, journey, and history of survival. But on the morning of December 8th, when Hubble's ultra-high-resolution images came back from its close study of 3i Atlas, one feature stood out above all the others. There were no craters, not one. From pole to pole, across every visible panel of its slowly rotating body, 3i Atlas displayed a surface so smooth it bordered on unnatural. The texture varied slightly between zones. Some areas showed faint ridges, others had soft linear contours, but there were no signs of chaotic trauma. No jagged impact sites, no ancient scars, no impact melt, just perfection. That discovery sent shockwaves through the teams analysing the data, because even the most pristine-looking bodies, like some outer moons of Jupiter or Saturn, still carry small-scale damage if you look close enough. Dust strikes are constant even in the outer reaches of the solar system. No object that has travelled this far, this long, should remain untouched. So how had 3I Atlas done it? Was it young? Recently formed? Unlikely. Its interstellar trajectory and chemical composition suggested age, ancient age, and if it had spent that much time moving through the galaxy, it should have encountered thousands, if not millions, of impacts. The second theory was composition. Maybe the surface had self-healing properties, like a gel or reactive polymer that restructured after each hit. But again, that kind of material behavior doesn't occur in known natural chemistry, let alone in frozen interstellar objects. Then came the third possibility, shielding. What if the object had been protected? Not passively, but actively. What if something prevented collisions from ever making contact? A field? A deflection mechanism? A form of surface armor that redirected or absorbed incoming objects before impact? Some scientists proposed magnetic deflection, similar to how Earth's magnetosphere protects us from solar wind. But that only works on charged particles, not solid debris. Others suggested electrostatic repulsion or a plasma sheath, exotic ideas, but still within the realm of theoretical engineering. The fact that these theories were even being entertained said everything, because the absence of craters wasn't a small detail. It was a data-backed fact. 3I Atlas was impossibly clean. As analysts overlaid the Hubble visuals with LiDAR depth maps and infrared heat distribution, they confirmed what the images implied. The surface wasn't just smooth, it was undisturbed. It hadn't been chipped, cracked, or pitted. There were no signs of erosion, weathering, or particle buildup. It was like a vehicle that had just launched yesterday. If this were a comet, it would be the most pristine comet in recorded history. But if it was something else, something built, then the smoothness made sense. In engineering, smooth outer shells are used to reduce friction, to shield vulnerable systems, and to prevent unwanted buildup. From spacecraft to submarines, form follows function. And in that context, the unmarked skin of 3I Atlas didn't look accidental. It looked intentional. One analyst, reviewing a zoomed-in panel of the mid-latitude surface, whispered what many were starting to think. This isn't erosion-resistant, it's impact-proof. And that changed everything, because a comet cannot choose to remain undamaged, but a probe could, a ship could, a message could, and if 3I Atlas has no craters, then it's never been touched. Not by rock, not by dust, not by time, and maybe that's the point. By the end of December 8th, after the final imaging data from Hubble had been collected, compressed and shared across networks of observatories, something unusual began to happen. The theories stopped. The press briefings quieted. The excitement faded. Not from disinterest, but from something else entirely. A kind of silence took over, because at this point, no one knew what to say anymore. For months, 3I Atlas had been the subject of intense scrutiny. Teams raced to classify it, to map its composition, to simulate its trajectory, to decode its jets, its spin, its reflectivity, its tail, its structure. And now, after dozens of anomalies and impossibilities, after readings that contradicted decades of astrophysical understanding, after behaviours that resembled machines more than rocks, a new atmosphere had entered the room, resignation, not out of defeat, but out of quiet realization. That this object might not be understandable in time, that it might not respond to our current models, that it might not want to be understood. Internally, the phrase passed from one observatory to another. Just keep watching. No bold papers, no urgent calls for reclassification, just observation. Because what else can you do when you're staring at something that refuses to obey? Across every space agency, from NASA to ESA, from JAXA to private observatories, teams are watching now with a different posture. Not to predict, not to explain, but to witness. This change is subtle but profound. Scientists by nature ask questions. They propose mechanisms, test against them, refine, repeat. But 3I Atlas doesn't reward that approach. The more you measure, the more it contradicts. The more you isolate variables, the more it invents new ones. And so the posture shifts from active analysis to passive attention. It's no longer about what it is. It's about what it does next, and that shift has already altered protocol. New observatories have been added to the daily tracking net, high-resolution imaging time has been extended, a silent alert has been established across several monitoring teams. No flashing alarms, no red flags, just a shared rule. If something changes, we need to know immediately, and so, they watch. Every night, every hour, data flows in, most of it confirming what they already know. The spin hasn't changed, the jets still fire in symmetry, the light pulse continues, the arc remains fixed, the polar axis stays dark, the tail bends without cause, the core delays still stretch, the surface is still impossibly clean, and still, nothing breaks, nothing fails, nothing evolves in the way natural bodies do. No fragmentation, no sputtering coma, no visible decay, just motion, silent, predictable, purposeful. In private, some researchers have compared the experience to being watched back, as if the object isn't just a curiosity in our sky, but a presence, moving not randomly, but with quiet confidence, on a path that doesn't seem improvised, as though it belongs somewhere and we are simply in its way. But officially, no conclusions, no statements, no classification updates, just one line, repeated in meeting notes, Slack threads, mission briefings. For now, we're just watching. And maybe that's all we can do, because there are moments in science when the unknown doesn't invite explanation. It invites patience. And if 3i Atlas is what some quietly fear it might be, a probe, a relic, a visitor, then watching may be the only move left on the board. We're not ready to reach, we're not ready to speak, so we just wait, silent eyes pointed skyward, every night, waiting for the next frame,